G'day, welcome to lecture 1.5 of Unit 2 Transmutation. Here is your learning intention and success criteria. Please pause the video and complete the knowledge and skills table. Okay, so having a look through here in terms of the knowledge, we should have identified, well, we need to know what is artificial transmutation, because that's what it's asking us to describe or define. We've got a few words under identify. The only one that should be new is this word, what is a deuteron? So we need to know what that is. And the word following it is bombardment, so we probably want to know what that means as well. In terms of skills, the ones we have here is the construct verb there. We know what a balanced nuclear equation is, but what it looks like underneath bombardment is slightly new. So we need to know, can we construct a bombardment type equation here, and we need to balance it as well. So the word transmutation, let's start with that. Now, the word transmutation means to change what something is. It comes from the word transmute, which means to change form or shape. Now, you've seen transmutations with the nuclear decay, where after emission the daughter nucleus left behind had changed from what it is. So in this example, we have uranium-238 here is transmutating into into thorium-234, and it's also spitting out an alpha particle and some gamma radiation, as we saw in a previous video. Now, when the syllabus uses this word transmutation, what they generally mean is artificial transmutation. That is transmutation that we humans forcibly do to an atom. Okay, so when we talk about artificial transmutation, we're talking about the purposeful collision of two atoms, okay, to make something new. So we're going to shoot an atom, or maybe a part of an atom, at another atom, smash them together, and make this original atom change. Now, the syllabus doesn't have any specific techniques mentioned, but there are a few in the text, and so anything new that pops up down the track will just be an extension of this same core idea, and this will help us with the ideas of nuclear fission and nuclear fusion when we look at that shortly as well. Now, the four mentioned in the text are proton bombardment, alpha bombardment, deuteron bombardment, and neutron bombardment. Okay, now the word bombardment means that we're going to hit it with it continuously. We don't just use one single atom or one single proton and shoot it at it. We shoot a lot of them, because this thing is a very random chance occurrence. You need to do a lot of them to make it happen. It's kind of like, if I've got someone standing in a dark room and I want to throw bean bags at them until I hit them, well, I'm going to have to throw a lot of bean bags because I don't know exactly where they are. So we have to do it a fair few times. Now, they all have their advantages and disadvantages, and the text has some information on that you should have a read through and peruse and summarise. It's fairly straightforward. What we're going to do is focus on how to use them today. Now, three of those, alpha, neutron, and protons, they are exactly what they sound like. Either we smash a neutron into it, a proton, or an alpha particle, and you've seen an alpha particle. And those nuclear equations will be fairly straightforward. A deuteron is something new, and you haven't seen that, and this is the nucleus of a deuterium atom. So deuteron is the center, deuterium is the whole atom, and this is the special name we give to hydrogen 2. So you may definitely want to write that down, that a deuteron is a hydrogen 2 nucleus, given the symbol 21H. Technically we should say 21H plus, and put a +1 next to it, because it is just the nucleus. However, the text actually doesn't do that, so you probably don't need to worry about it too much. So let's look at some nuclear equations. Now, the good news is, or the bad news possibly, is that there are no easy predictions for any of the bombardments. So that means you're going to get questions that would be like fill in the blank. And there are a couple of them in the 6.1 questions. So I'm going to go through some of the examples inside the text using that style. Let's load up pen. So let's firstly do a proton collision. Now, when we do a proton, technically a proton is a hydrogen atom, but generally we write that as a 11p. The top one, remember, is the nucleon count, and if there's only one proton, there's only one, and the bottom p is for the proton, so the bottom number is for the proton count, and since it's a proton, there must be one proton. So if we collide this with a 7,3 lithium, and we produce helium gas, 4,2He, and there'll be some gamma radiation comes out as well. what's the atom that is missing? Now we do exactly the same thing that we've done with our alpha decay and our beta decay equations. We add up the top row and we add up the bottom row. So if I have 1 plus 7 over here, that's 4. Sorry, 1 plus 7 is 8. 4 here, well 4 plus what equals 8? It must be another 4. So I could do 1 plus 7 take away 4, or 1 plus 7, 4 plus what, and work it out myself. On the bottom here, 1 plus 3 is 4, take away 2 leaves me with 2. And so I would end up with another helium particle there. Okay, so again, we make sure the top adds up, we make sure the bottom adds up. If we wanted to look at an alpha particle collision, and alpha particle collisions are really important whenever you're studying anything about stars, because stars use extensive amounts of helium collisions in order to model these. So let's take a 4,2 helium crashing into a nitrogen 14. Okay, this would happen, so there should be a plus there. This would happen in the sun, and would happen in some larger stars as well. And it's going to create, let's see, a 17, 8 oxygen. But let's see if it's balanced. We have 4 plus 14 is 18, and this one with 17. So we're going to need, there has to be something left over. 2 plus 7 is 9, but we've got 8, so there has to be 1 left over. We have a 1, 1 here, which we know is a proton. You could write hydrogen, because it is hydrogen, but the text in this case is saying, well, it's a proton that's been left over. I'm not really going to worry too much. If you write P for proton or H for hydrogen, they mean the same thing. It's not a big worry. So this is the idea of smashing an alpha particle in. Okay, we're going to change some of the counts, and we're going to have a bit left over. Sometimes it'll be a proton, sometimes it'll be a neutron. It just depends on what you smash into what. Let's have a look at a deuteron equation. So here, let's do this one. This will be relevant because we talked about this today. So one way of making gold is to smash a deuteron, okay, so a hydrogen 2, into an isotope of mercury, mercury 199, and you are going to get 197.79 gold, plus something left over. So let's have a look at the numbers here. We have 2 plus 199 is 201, 197 plus something is 201, well the difference will be 4. 1 plus 80 is 81, 79, the difference would be 2. So there is also some helium gas that's being produced there. But another one here, another example is smashing a deuteron atom into a platinum atom, which is 78. It creates gold, 197, but it leaves a neutron left over. As I said, you're not going to be able to know exactly, you're not going to be able to say exactly, oh, this is what it's going to make. You're going to have to do some fill in the blanks more often than not, unless they specifically tell you that, oh yeah, these two things collide and it makes one single atom. So let's have a look at that with a neutron example. There is one here. They have a 238 uranium atom plus a neutron will give us, and they say here, well, it's going to make one single atom, and so in this case it makes a 239 uranium atom, which should be very unstable and would decay, okay, if not split. Okay, so these things are all examples of artificial transmutation, where we purposely, and that's why we've got the addition of two things here on the reactant side, we have two things that smash together in order to create something new. What's left over though, and sometimes there won't be anything left over, you're not going to be expected to know this. Okay, none of these would be expected things, because none of these particular techniques, proton collisions, alpha collisions, deuteron collisions, or neutron collisions, none of these particular techniques are mentioned in the syllabus as being required to know about. Okay, but you should have some basic understanding of some of them, so you can use one of them as an example. The things you do need to be able to distinguish between these two, okay, that is in the syllabus. Now remember, both of these involve transmutations. There is the change of one atom into another. It doesn't matter if it's decay or artificial transmutation, it's still a transmutation. Okay. Natural decay, though, always involves something being ejected, at least for the contents of our syllabus. Either going to be an alpha particle, it's going to be a beta plus or a beta minus particle, but something comes out of the nucleus. It is losing mass. Okay. Essentially. And I say that because we haven't got to calculating masses yet. Okay. Artificial transmutation, though, involves us starting a reaction by shooting another particle into it. Okay, and so then that causes the change. So you do have to be able to say, well, they are similar because they both involve transmutations, but the natural one involves ejection, while the artificial involves insertion. Okay. So, in this video, we have gone through a couple of things. We've defined this word transmutation. We've identified 4 types of nuclear bombardment, and we've done some balancing equations with this nuclear bombardment. So hopefully that didn't seem particularly difficult. For revision for this, for your interceptor class, complete questions 1 to 4 from chapter 6.1, and copy your answers into the 2.1.5 space on eLearn. Thanks for listening, guys. Have a great night.